This is section 4.1. It's just a one-day video for the section, and we're looking at this. We're going to look at this question really throughout this entire unit for chapter or for 4, and that is the derivative. Now that we can calculate it, what is it good for? So what can we use it for? So our essential question then for today is how can derivatives be used to locate extreme values? So that's one of the things that the derivative is useful or good for, is finding these extreme values of functions. So you might be asking, well, what exactly is an extreme value? So we can look at extreme values. These are global extreme values, and those are absolute maximums and absolute minimums. So in another word, we could call the absolute maximum value that biggest y value. So it would be like a hill, and the absolute minimum value might be like a valley. That would be just one example. And so we're talking about a maximum that all other values are less than or equal to that value. And for a minimum, then we're saying here all other values are greater than that minimum value. And there can only be one of each on each function. That's why we call them global. There's one max and there's one absolute min. So let's take this function for example. We can just do this visually. So the extreme values can be on the interior or at the endpoints of a function. These endpoints go off into infinity. So in this case, we can't have an extreme value at the endpoints since it goes off to infinity. So if we look at this, we visually can see that there is an absolute minimum right here at the vertex. No maximum since these go off to infinity. The domain here is from negative infinity to positive infinity. So we know we've checked the entire function, so to speak. Let's take a look at this portion of that, of x squared. So now I've restricted the domain to start at 0 but not include 0, and to end at 2 and include 2. So in this situation, we don't have a minimum because we don't have a closed circle here at 0. So there's technically no minimum value. In other words, we can approach this 0. We can approach this value, but we can't ever attain this minimum value. So we can't ever attain a smallest number because we can always get a little bit closer. And then the maximum is up here, and it's up here. The maximum value is 4. We've got a colored in dot. We can reach that maximum value. So there's our absolute maximum, our biggest of our big, so to speak. So let's further restrict the domain, have open circles at both 0 and 2. And in that case, we have no min and no max to this restricted function. So we have this extreme value theorem then. We say if f is continuous over a closed interval, then f has a maximum and a minimum over that interval somewhere. So for instance, we have to have continuity, and the interval has to be closed. In other words, we need filled in endpoints. So here we go. Here's an example of a function that's continuous and has closed endpoints. It's the closed interval. And so there has to be a max and there has to be a min. So visually we can see that we have a min right here and a max right there. And so if we change the function to look something like this, then we have a maximum and a minimum still, and they happen to be at the endpoints. And then we could have something like this, where we have a maximum and a minimum, but the maximum happens to be at an interior point, and the minimum has to be at an endpoint. Happens to be at an endpoint. So here's my minimum, my global minimum. Here's my global or absolute max. So if we look at these functions algebraically, then we know what this looks like. We've seen it already in the PowerPoint. We're going from negative infinity to positive infinity, so we know we have no max and we have a minimum at y equals 0. And for this one, that's a This is going to be an upside down parabola, and so kind of a frown. And so we're going to have a maximum where that vertex is, and that vertex is at 2. And then we're not going to have any minimum because the domain isn't restricted. And then we know what sine x looks like. If we have our graph here, it's that oscillating starting at 0. And we're going to go from minus 2 pi to plus 2 pi and not include the endpoints. So if we go from minus 2 pi to plus 2 pi, we've got 2 oscillations. We've got a max of 1 and a min of negative 1. And those maxes and mins occur multiple times, and that's okay. Okay, so let's talk about local extreme values. So the absolute is the biggest of the big and the littlest of the little over the entire function. Relative or local extremes are just, they're either maxes or mins in the immediate vicinity. So they might not be the biggest of the big or the littlest of the little, but they're the biggest in their local area, or they're the littlest in their local area. So I call these like thinking about the neighborhood. So we're going to look for the biggest in the neighborhood and the littlest in the neighborhood. So that's kind of how I view the local extremes. So let's look at a couple of examples. First of all, there can be several of each. And if we look at our absolute extreme, our biggest of our biggest and our littlest of our littlest, those also can be called locals, but we typically don't refer to them as locals. We refer to them as the absolutes. Okay, so let's just take this generic function here. It's a continuous function, but it has a cusp right here, so it's not differentiable right here, but it is continuous. We don't have to lift our pencil in order to draw it. So let's talk about absolutes. So here's our absolute minimum. It's the littlest of the littlest. And here's, it's also a local. I mean, it's also the littlest in this immediate vicinity. But since it is the absolute minimum, we don't typically call it a local. Here's a local max. So as we're traveling to the right on this function, we hit a hill. It's a local max. It's not the biggest value, because the biggest value is over here. But it is the biggest in this immediate vicinity. Everything in this immediate vicinity is smaller than it. So we call that a local max. And using the same sort of logic, then this is a local min. It's not the littlest. The littlest is way over here at the beginning. But it is the littlest in this immediate vicinity. Everything around this is bigger than it. So it's a local min. And then we come over here. Here's our absolute max. It's our biggest of our big. It's also a local. You know, everything in this area is definitely smaller. But since it's the absolute max, since it is the biggest of the big, we refer to it as an absolute max. And then we get to the end point here. And so this end point is a local min. So in other words, everything around this end point is bigger than it. It's not the smallest value overall, but it is the smallest value in this immediate vicinity, so that's a local minimum. So that's kind of the distinguishing between absolute and local. Remember, absolute are also called global, so we could call this global, the absolute maximum, and locals, the local maxes, or the local maxes and the local mins are those locations, and those are also called relative. So we could call these locals relative as well, relative extrema. Notice that all the local extreme values are on the interior. Okay. So we talk about local extreme values. They recur when the derivative is either 0. So we notice we have a derivative of 0 at hills and valleys. Right? Our tangent line is 0. Or where the derivative is undefined. So we have this cusp here. And the tangent line is positive coming into the cusp, but negative leaving the cusp. And so since we have 2 different tangent lines that could possibly be drawn at this location, like here's our local max, there's our tangent lines, those are horizontal. Oops. but I guess I don't have these drawn here. But this tangent line is positive and this tangent line is negative, so it's not defined. So the local extremes that are on the interior of the function, they're occurring. Like, I mean, we have locals here and here as well, but specifically here. This is a global. But these locals that are on the interior, their derivative is either 0 or the derivative is undefined. And that's how we're going to algebraically find extrema on the interior. And we'll get to that in just a little bit. So let's take a look at this a little more carefully. We know we have a local maximum there, okay? And that's where we have a tangent line that's horizontal. And we know we have a local minimum here, and we also have a tangent line that's horizontal. So we have this extreme value definition here. It says if a function has a local max or a local min, in other words, if it has a hill or a valley, and it's on the interior, and it will be on the interior, then the derivative does exist and the derivative is 0. So the derivative of the function here is 0 and here is 0. That interior point, these locations, we call that interior point C. So the derivative at point C, so it could be here, here is 0. And the derivative does exist. Okay. So if we take a look at just this all wording in total, it says a function f has a local max. So if function f has a hill or a valley at an interior point, and if the derivative exists, then the derivative is 0. So that's kind of what we're saying here. Here's a hill, here's a valley. The derivative does exist, and so those are 0. So this is not 0 because the derivative doesn't exist. Remember, this is a cusp. And so we have a derivative that's negative coming out of it. That's the right-hand derivative. And we have a derivative that's positive going into that cusp. That's the left-hand derivative. And those two values are not the same. That's a cusp right there. So this derivative is not equal to 0. It's undefined. Okay. It is also a local extrema. Remember, our definition of a local extrema is either the derivative is 0 or the derivative doesn't exist. So now we're going to talk about critical points. This is a point in the domain of a function at which the derivative is equal to 0 or the derivative does not exist. Is called a critical point. So I'm going to back up a slide here. This point, and this point are all called critical points. Hills, valleys, and cusps and corners. Okay, so, and then just a quick note here, maximum and minimum points in the interior of a function always occur at critical points. So maxes and mins, hills and valleys, cusps and corners always occur at critical points. But critical points are not always maximum and minimum values. So let's talk a little bit about that. So let's talk about finding extreme values when we're talking about this. Finding extreme values analytically. In other words, how do we do this mathematically? So we're gonna kind of follow this 5-step process. We're gonna find hills and valleys. We're gonna find cusps and corners, and then we're gonna find their y values. Okay, so the extreme values we need to find those cusps, corners, hills, valleys. And then we need to talk about endpoints. So, and we're going to use a number line to kind of describe all this. So we're going to go after the hills and valleys, and those hills and valleys are where the derivative equals 0. So here's a hill, here's a valley, and so we'll do this analytically in just a second here. So we're going to set the derivative equal to 0, and we're going to solve for those locations, and then we're going to find cusps and corners. So, so we're going to set the derivative equal to 0. That's why we have a 0 as the derivative value. And we're going to then, we're going to find those x locations. And then we're going to look for cusps and corners. So visually we can see a cusp here. Okay, and that's where the derivative is undefined. So we're going to look at our derivative function again, and we're going to see if there's a location where it wouldn't be defined. like let's say the derivative is a fraction, then it wouldn't be defined where the denominator is equal to 0. So we're going to find those locations. And like I said, here's one example. So we'll find that we'll just stick a u on the derivative number line when it's undefined. So now we've got derivatives that are 0 values, hills and valleys. We have derivatives that are undefined at cusps and corners. We can find the y values. So these two are the critical points. We're going to find these y values then. So we're going to take these x values, stick them back into the function, and find some numeric answer. Right, take the x values, plug them back into f of x, not the derivative, but the regular function. And we're going to find these values, these y values, and we're going to stick them on that number line. Okay, so this will give us numbers that we can compare to see which one's the biggest. And then we have to look at the endpoints. So we have to find the y values at the endpoints. So if we look at this function, we've got an endpoint here and we've got an endpoint here. We're going to find those numbers by taking by getting their y values. And then we can look at this whole this entire number line for function values. And we'll be able to find, we'll have these 1, 2, 3, 4, 5 numbers here. Okay, so we've got the pink numbers, which are our endpoints, and the green numbers, which are our critical points. And we can just visually look at those values and figure out which one's the biggest and which one's the smallest. And for our absolute max and our absolute min. And then the rest are just locals. And so we're going to kind of follow that process. So we scan this number line, we'd see this would be the biggest number. We could label that an absolute max. We'd scan the number line again. We'd see this as the smallest number. We'd label this an absolute min. And then the rest, this would be a local, this would be a local. And this would be a local. I don't know why I didn't label that, but this would also be a local at the right endpoint. Okay, so let's try this with an actual function. So here's the actual function, x cubed minus 12x plus 4. And we can see the function right here. So we can find the absolute max. We can find the absolute min. We actually have 2 locations where we have an absolute min. And then we can find local maxes and stuff like that. But let's do this analytically. So first, we're going to find the hills and valleys. So we're going to take the function and find its derivative. Okay, so if that's the function, x cubed minus 12x plus 4, the derivative looks like 3x squared minus 12. We're going to set that equal to 0 and solve that. So we're going to factor out a 3. We have x squared minus 4, and then we factor this. We don't put the 4 on the other. We could put the 4 on the other side and take a square root. And I guess that's what I do. But when we take that square root, please be sure to remember to put a plus or minus there. I would actually prefer this factored into x plus 2, x minus 2. I think that's a little more telling as to what the critical points are. So we have critical points at 2 and negative 2. So we have a critical point right here, and we have a critical point right here. Remember, those are on the interior, right? When we set the derivative equal to 0, we're finding these points on the interior. And so we're gonna locate those. There are my critical points. So I know I have a 0 derivative. Remember, this is the derivative number line. These are derivative values. The derivative is 0 here because it's a hill. The derivative is 0 here because it's a valley. Okay, so we're done finding hills and valleys. Now we're going to find cusps and corners. These are also called critical points. So if we look at the function and its derivative, I guess I don't list the derivative, but the derivative is 3x squared minus 12. That derivative is not a fraction, so there's no cusps or corners to look for. So we can just go right on to step 3. We're going to find all the y values. So we're back using this function, and we know we have to look at x equal to negative 2 and x equal to positive 2. So here's the function. When x is negative 2, y is going to be negative 2 cubed minus 12 times negative 2 plus 4. And that's going to equal negative 8 plus 24 plus 4, that's going to equal 20. So we have a y value of 20. So I'm going to put 20 on the function number line. And now we have to look at when f is 2. So when f is 2. When x is 2, we have to look at the function value. So we're going to plug 2 into the function value. So that's going to give us 8 minus 24 plus 4. And so that's a minus 12. And so I'm going to put a minus 12 on my function number line. So now I've got my y values, and I can see that 20 is bigger than 12. So 20 must be a max, and 12 must be a min. We just don't know if they're global or if they're local. We'll figure that out in just a minute when we look at the endpoints. Okay, so but those are the critical points, negative 2 comma 20 and 2 comma negative 12. Okay, let's find the y values for the endpoints now. We have a closed domain at negative 4 and 3. So we need to find f of negative 4. And when we plug it in, it looks like that. And the answer is negative 12. Okay, so I'm going to put that on the function number line. And then we're going to find f of 3. So we're going to plug 3 into the function. Remember, we're plugging all this into the function. We're finding function values. And so that is going to be negative 5. So I'm going to put that on the number line. And so now I've got all of my y values. So now I can scan this. And I can see what the biggest of the big are and what the littlest of the little are. Okay. So we're going to start organizing our information and finding our extreme values. Okay, our y values. And where they occur. Our x values. So our absolute extreme, we're using the number line. Our absolute max is right here. 20 is the biggest of the big. And that occurs at x equals negative 2. So there's our absolute max. Our absolute min is negative 12. And that occurs at 2 locations. It occurs here at negative 4 and here at 2. So there. And our locals. So not absolute. So anything else that we haven't listed yet. So that's got to be at y is equal to negative 5. And we know that is an x value of 3, and that's a local max. So this endpoint right here is the biggest in its area. So we call that a local max. So that's one example of having a polynomial function and finding our extrema over a closed domain. There are no local mins. We've used all our y values, and there's nothing left to evaluate. So we have no local mins, technically. We could call the absolute mins local if we wanted to, but we don't typically double name things. Okay, let's take a look at this one. Here we have a function that is x to the 2/3 power plus 1. Notice I haven't drawn it. Okay, and I'm being specific because I want you to rely on the analytical method here. So we're going to find the hills and valleys. So we have to take the derivative and set it equal to 0. Okay, that's what we have to do. That's our strategy. And so here's our function. So its derivative then is to do the power rule here. Bring down the 2/3, x to the minus 1/3, that's 1 smaller, and then plus the derivative of 1 is 0. So here's our function, our derivative, and I'm going to rewrite it. And notice the derivative this time is a fraction. So we're going to have the possibility of it not being defined. So our derivative is 2 over 3 to the cube root, 2 over 3 times the cube root of x. So when is that equal to 0? And the answer is, well, 0 is really 0 over 1, and we could cross multiply here if we wanted to. But really what we're saying is 2 is equal to 0, because 0 times this is 0, which never happens. So it's never equal to 0. So in other words, we never have a hill and we never have a valley. So no hills, no valleys. So notice our number line stays blank because we've got nothing to put on it. Now we're going to find cusps and corners. So remember, our derivative looks like this. And so we want to know where it's undefined. And undefined means the denominator is equal to 0. So we're going to set this denominator equal to 0 and solve it. Okay, so we can divide each side by 3, and we'll get the cube root of x equals 0. And when we cube everything, we get x equal to 0. So we have an undefined derivative when x is equal to 0. So I put undefined here. And so that means we must have a cusp or a corner here. So let's find the y value. We only have one location where we need to find the y values, and that's at when x is equal to 0. So when x is equal to 0, the y value is 1. And so we know that we have a point then, a critical point at 0, 1 right here. So that's our critical point. So you might be guessing what this looks like now. And we're going to get to drawing it in just a second, but we're going to need the endpoints in order to draw it or to sketch it. So this is a closed domain. We've got one critical point here. We know it's a cusp or a corner because it's where our derivative is undefined. Now we have to look at the endpoints to see if the endpoints are above this or below this. So we're going to plug in -2. And so when we plug in -2, we have -2 to the 2/3 plus 1. So this is a calculator. -2, use your caret key, put the 2/3 power up there, then add 1. And when you do that, that gives you a value of the cube root of 4 plus 1. So we know that it's 1 plus another, plus a little bit. So we know that at -2, we're up here, and it's about 2.7 or so. It's about 2.6, 2.59. Okay, so that when we plug in 3 then, we've got 3 to the 2/3 power plus 1, which is the cube root of 9 plus 1. And the cube root of 9 is not 3. Okay, it's something else. So when we evaluate that on a calculator, we get a value that is about 3.08. And so we know that these are the two values at the endpoints. So we know that this function now, okay, is, we're just going to start organizing our information here. We know that the extreme values here, if we're just scanning the number line, the biggest of the big is over here at the right endpoint. The littlest is right here when x is equal to 0. So we're going to get those y values and where they occur. So the absolute extremum, we're going to look at that number line. Our max is going to be 3.08, and that occurs out here at the endpoint, x equals 3. Our absolute min is 1, and that occurs when x is equals to 0. So there's our absolute min. And we have a local extrema here, not absolute. And we know that, that's a local max because we have to, this has to be, since there are no other mins or maxes defined, this point, the values have to go directly down to this point. So that's a local max at 2.5, a y value of 2.59, which is an x value of -2. So no, that's a local max. So if we know, since we've used all of these endpoints, we know that we have no local min. So there's the sketch. So if we look at this, we know that x to the 2/3 plus 1 is not linear. So we draw a gentle smooth curve to this cusp, and then we draw a gentle curve out of that cusp. We know, so when I would grade this as an AP grader, if I asked you to sketch it, what I would look for is I would look for a cusp. We know this is a cusp, so we know we have to come in and curve in this fashion, and then we have to curve out of that fashion to create that cusp. We couldn't curve the opposite way; that wouldn't make a cusp. And so I would just look for something that doesn't look linear for grading for credit. Okay, so here's another one. Let's take a look at y equals -e to the x. So, and we're going to look over the domain of -1 to 1. So -1 is this. I've really zoomed in here. -1 is way over to the left here, and 1 is way over to the right. So we're going to find the hills and valleys. So let's set the derivative equal to 0. So if the function is e to the -x, then our derivative, we'll need the chain rule here, is going to be e to the -x times -1, which is going to be -e to the -x. And so when is that equal to 0? That's really the question being asked. And so I'm going to think of negative e to the negative x as negative 1 over e to the x. And that, like the other example, we could cross multiply. We have negative 1 equals 0. That never happens. In other words, in order for this to be 0, I'll come back to this expression, the numerator has to be 0, and the numerator is 1. It'll never be 0. So we know we have no hills and valleys over this domain. Okay, and so let's see if there are any cusps and corners. So again, the derivative is negative 1 over e to the x. So we're looking for where this is equal to 0. And so where is e to the x equal to 0? So we're looking for cusps and corners. We're looking for an undefined derivative. Derivatives are undefined when the denominator is 0. And so when we're looking at e to the x equals 0, there's never a possibility for this to equal 0. E to the 0 is 1, so that doesn't work. And any negative or positive value of x will not give us a 0 value. So not only are there no hills and valleys, there are no cusps and corners. So we have no critical points. We have no hills and valleys, we have no cusps or corners. So we have nothing on our number lines yet. So finding the y values, well, we're not finding any because we have none. We don't have any hills and valleys, we don't have any cusps and corners, we can't find any y values. So we move on and just start looking at the endpoints. We have a closed domain, and so we have to find the value at the endpoints. So the value when x is equal to negative 1 is e to the opposite of negative 1, which is e to the 1. So that's about 2.7. So here's at negative 1, we have a y value of about 2.72. And at positive 1, we have e to the opposite of 1, which is e to the negative 1, which is 1 over e. And 1 over e is about 0.37. So the left part of our domain, we're up here at 2.72. The right part of our domain, we're at 0.37. So, and since we have no hills, valleys, cusps, and corners, we have to just have a gentle sloping function from the left point to the right point. So as we organize our values now on the number lines, we don't have any 0 derivatives, we don't have any undefined derivatives, so our derivative number line is still blank. But we need to we need to look at these y values, and we need to find out where they occur using the number line. So our max is 2.72, that's our biggest value, and that occurs at negative 1. Our absolute min is 0.37, that occurs at positive 1. We don't have any locals. And so we're going to just draw a gentle sketch from the max to the min. And this is the one point where we need a little more information. We don't know if we should draw it sloping like you see or sloping the other direction like this. Okay, and so that's a difficult decision to figure out. And in order to figure that out, we need to look at the derivative a little more carefully than we are right now. Right now we're just looking for 0 values, but we actually have to look at what a derivative value would be in between. So that being the case, then, and that's going to we're going to kind of figure that out as we go into section 2. But for right now, for this example specifically, we know it curves like this. This is a decay sort of curve, where an e to the positive x would be an exponential growth. So that kind of takes care of locating extreme values, and you know, we're going to keep following that 5-step process. We're not going to take shortcuts on that. And in fact, the next day, to finish up for one, we're going to do an anchor chart, so we have that 5-step process detailed on an anchor chart. So at this point, then you can go ahead and do the day 1 homework for section 4.1.